In this session, we will discuss the properties of the wave and the three properties which we will discuss, that is reflection, refraction, and diffraction. A quick revision what we have discussed yesterday. So we started with the concept of the proper waves. What is a wave? It's a way by which energy transfer from one place to another, and the waves can be wave transfer energy from one place to another, and the disturbance moves along the wave, not the particle. Like you can see a water waves, the particles are vibrating and they're transferring the energy from one place to another. On the basis of particle vibration, the wave is divided into two categories. One is known as transverse, another one is longitudinal. Transverse means when the particles of the wave are vibrating perpendicular to the direction of the wave, like particles are moving up and down and the wave travel towards right or left, we call that as transverse. And in a transverse wave, these are some examples of the transverse. So transverse wave, the amplitude, the height of the wave is refers to the amplitude. The distance between the two successive crest or trough is known as the wavelength. So we have already discussed this part. Then the frequency means how many times the particle are moving in 1 second or vibrating in 1 second. So number of vibrations completed by the particles every second, that is known as the frequency. So at the first one, they vibrate in 10-second interval, they're vibrating 10 times, the frequency is 1 hertz. But the second one, they're vibrating 14 times in 1 second, so the frequency is 1.4 hertz. And the last one, they're only vibrating 5 times in 10 seconds, so the frequency is 0.5 hertz. The period means the time it will take to complete one vibration. We call that as a period or time period. And time period and frequency are inversely proportional. We want to calculate the speed of the wave, so we can use the formula V is equals to F lambda. This is a very important formula. It can be used for any kind of wave. This already we discussed, the example question. The longitudinal wave, the wave in which the particle vibrate parallel, as you can see, the disturbance of the particle is same as the direction in which the wave travel. Example of this wave is a sound waves, and the region in the longitudinal wave, their particles are closer, we call compression, and where the particles are away, we call that as rarefaction. Now today's topic is about the properties of the wave. So to study the properties of the wave, what we do, we use a ripple tank. This is a tank. There's a tank. The base of this tank is made up of glass. This is a glass, and this tank is filled with water. Like there's a water inside here. So what we do, we produce a wave. The water waves are produced by any source of vibration. We produce the water waves, and top of this there's a lamp, a bulb is there. So what is the purpose of the bulb? When it produces light, the light will pass through this wave and it will create a pattern on the screen which is there at the bottom. So as the light is passing through the water, it will create an image, it will create a pattern at the base or on the screen, so we can observe the waves. Like here you can see, this is what, like example, we have a ripple tank. This is a ripple tank, and we produce a vibrating object here. Like we place two vibrating objects. So what we'll see below the image on the screen, so how it will appear like this. So this is the image which is created, a ripple image of the ripple or the waves which is created in the ripple tank. Is it clear the concept? What is a ripple tank? A ripple tank is a simple tank which is having a glass base, and when we disturb the water and passing the light, the top of this the light is placed. So when we are passing the light, as a result, it create an image at the base. This is the image, this is not the water, this is the image which is created by the ripple tank. And what we call these lines, these lines, what you see, what we call them, these lines are known as wave fronts. As here you can see this line. So these lines are known as wave fronts. The line which is representing the identical, the lines or the points which are representing the identical phase, we call them as wavefront. This is another image just to make you understand. As you can see, this is a ripple tank, so the vibrating object is here. Maybe that might not be clearly visible, but there's a vibrating object. If you try to focus on the image, then there's a vibrating object which is moving up and down. So as a result, when this vibrating object is moving up and down, it will, and the lamp is placed. I did not show the lamp here in this image. So lamp is placed at the top of it, and we'll see the image at the bottom below this. And what we call these lines, the lines which we see here, these lines, what we call them? We call them as wave front. So this is also a wavefront. So in a ripple tank, we basically have a vibrating object. This is also a ripple tank, but this is a large scale, like is ripple tank, which can produce big waves. But a normal ripple tank, which we are using in the lab, it's a very small size ripple tank. But this tank is also a ripple tank as it is producing a wave. So why we use water specifically to study the wave property? Number one, because water waves are easy to produce. Like if I want to produce the water waves, what I have to do, I just have to vibrate any object. I can vibrate to and fro or up or down. So it will produce the water waves. So water waves are easy to produce and we can see them. We can observe them. But why not sound? Why we did not use sound? Sound is easy to produce, but sound waves we are not visible, like we don't see sound waves. That's why to study the properties of the wave, we use a ripple tank, and in the ripple tank is filled with water. As water we can see, so we will use it to study the properties of wave. The first property of the wave is reflection. What is the meaning of reflection? Reflection means when the waves strike the surface. Look, there are two things. This is a ripple tank. This is what is happening in a ripple tank. And the second image is what you will see on the screen at the below the ripple tank. So what is the concept of the reflection? Reflection means when the waves strike the surface, here we are producing a wave. Here we are producing a wave by vibrating object. So when it produces a wave, the wave will strike and the wave will bounce back. So this is what we'll see on the screen, the object. This is the object. So when we produce a wave, wave will travel. As you can see, the waves are traveling. And when these waves strike the surface, these waves hit and they bounce back. So when the waves strike the surface and it bounces back after striking a surface, what we call this property, we call that as reflection. So property of a wave to change the direction when it strikes the surface, we simply call that as reflection. So this is a top view from the ripple tank, and this is what we will see on the screen, because on the screen we'll not see the object, we'll see the image which is created by the bulb, the lamp on the screen. So this is the object. So when the waves strike this, it will bounce back or changes the direction. We will call that as reflection. Another example, like these are the wavefronts which are striking the surface. So the wavefront which strike the surface, the other wavefronts after striking a surface, they will bounce back. So property of the waves to strike the surface and bounce back, we call that as reflection. So only thing which changes when the waves strike the surface is the direction. The direction will change. The rest other things will remain same. Like the wave was coming from this direction. When it strike the surface, it bounced back. in opposite direction. Is it clear the concept of reflection of the water waves? So we are using a ripple tank to discuss the properties of the wave, as the water waves are easy to produce and observe. So the wave which strike the surface, that is called incident, and the wave which bounce back, that is known as reflected. This is another example, like the wave strike the surface and changes the direction. We call this as reflection. Is it clear the concept of reflection? Any doubt till this point? The second property of a wave is known as refraction. What is the meaning of refraction? The term refraction means when the wave travels from one medium to another, it changes the speed, and we call that as refraction. Example, if this is a ripple tank, this is, you're looking from the sideways, a side view of ripple tank. This is a ripple tank, and this ripple tank is filled with water, but this is not having the same depth, like it is not having the same depth throughout. One region it is deep, the water is deep, another region it is shallow, like smaller depth. So what we will observe, when the water is moving from deep region to shallow region, the water which is moving in a deep region, the water waves are able to move faster, but when it enter a shallow region, it will slow down, because in a shallow region less space or small space is available. So in a deep region the water is moving fast, and in a shallow region, because of smaller space, the water is moving slower. So moving from deep region to shallow region, as the speed of the wave changes, so whenever the wave travel and its speed changes, it can be decrease or increase depending on the question. But if the speed changes, what we call this property, we call that as refraction. So refraction means the property of a wave to change the speed when it travels from one medium to another, or one place to another. If the speed of the wave changes, we call that as refraction. And this is very common observation. Like example, if you are standing at a seashore, if you are observing the two waves which are far away from you in a deep region, they have a greater distance between them. But as they are coming or approaching towards the seashore, what you will find the distance between the two waves decreases, or the waves are getting slower, or they become slower. As they enter a shallow region, the wave speed decreases, so they will come closer to each other, and we call this property of a wave to change the speed when travel from one place to another as refraction. So this is a side view, but if I look the same ripple tank, if you are looking on the screen, if you look from the screen or the top view of the ripple tank, what we'll see, in a deep region, the wave fronts, they have greater distance between them. But as they enter a shallow region, what we'll see or what we'll observe, the distance between the wave fronts decreases. So as the distance between the wavefront decreases, it shows that the speed has changed. And whenever the speed of the wave changes, we call that as refraction. If the direction changes, we call reflection. But if the speed of the wave changes, we call that as refraction. Is it clear, the concept of refraction? Any doubt till this point? So example, you're looking from the top. This is a ripple tank. You're looking from the top. So The water enter from deep region, like water waves are there in a deep region. From deep region, they move to a shallow region. So in a deep region, you can see they're moving faster and they have greater distance between them. But as they enter a shallow region, the distance between them decreases. So if the distance decreases, so the waves slow down when they reaches a shallow region, and the wavelength also gets shorter, but the frequency remains the same. How the frequency remains the same? We have the formula V is equals to F lambda, or we can say F is equals to V divided by lambda. How the frequency of the wave remains same? Example, in a deep region, the water was moving with a speed of 10 meter per second, and it was having a wavelength of 5 meters. So when we find the frequency in a deep region, frequency is speed divided by wavelength. So speed is 10 and wavelength is 5. So frequency will be 2 hertz. As the water move from deep to shallow region means lower depth, so it slow down. So its speed decreases. Like example, the speed is now 6 meter per second. Its wavelength also decreases. The wavelength is 3 meter. When we calculate the frequency is speed divided by wavelength. So speed is decreasing, wavelength is also decreasing, but the ratio between them, like 6 divided by 3, will also give us 2 hertz. So what happen is the ratio between the speed and the wavelength remains same. That is why the frequency remain unchanged. The only thing which changes is the speed and the wavelength, but the frequency of a wave does not change even it travel from deep to shallow or travel from shallow to deep region. Is it clear this part? So what happened in a refraction in a deep region, you can see the speeds, the relative speed. So in a deep region, it is traveling fast. In a shallow region, it is traveling slow. And when it is traveling faster, the distance between the wavefronts is more. But as it slow down, the distance between the successive wavefront decreases as it moves from deep region to shallow region. So speed of the wave decreases, the wavelength decrease, but the ratio between speed and wavelength remain constant, or the frequency remain unchanged. If a wave is making certain angle, like example, it is coming with an angle. So when the wave travel from deep region to shallow region, what we will see, or what we'll observe that the wavefront will slow down and it changes the direction as well. In the previous example, it was not changing the direction as it was coming directly towards, so it was not changing the direction, only speed and wavelength changes. But if the incoming wave is making certain angle, then the wave will slow down as well as it will change the direction. So the only difference between the two is the first one, it was moving directly perpendicular to the boundary, but the second one, it is making certain angle. That's why it changes the direction as well. So what we will observe, like example, if we say this is a ripple tank, you will find this as a common question in which you have to draw the wavefront. Like if this is a ripple tank and one side of a ripple tank is a deep region, and the other side is a shallow region. So when it is, what is the direction of the wave? The direction of the wave is always perpendicular to the wavefront. So the wave direction in this manner. Now, the what happened when it is moving exactly perpendicular to the surface? This is a deep region, and here is a shallow region. So this whole wavefront will enter the shallow region. So when it is moving directly, So the whole wavefront will enter a shallow region. As a result, what will happen? The wavelength will decrease, but the direction won't change. In this case, the direction of the wave will remain same. Only thing what happened, moving from deep to shallow, what we'll observe moving from deep to shallow, we'll observe the wavelength denoted by lambda and speed both will decrease. But if the wave is making certain angle, like part of the wave is in a deep region and part of the wave is in a shallow region, so what will happen in that case? So this is a boundary for deep and shallow region, and the wavefront, these are the wavefronts. So some part of the wavefront is in a deep region and some part of the wavefront in a shallow region. Like this is a deep region and this one is a shallow. So when part of the wavefront in a deep and part in a shallow, what will happen in a shallow region? The wave will slow down. So how we represent the wave slow down? Look, if I draw same, it means it is moving at the same speed. If I draw tilted to like in this manner, it means it is moving faster. But because it's slowed down, so how I will draw? Not straight means they are moving at the same speed. If I draw in this manner, it means it is moving faster. But because in a shallow region it is moving slower, so I will draw other way around. And all the wavefronts which we draw should be parallel to each other. So here the direction of the wave is also changed. How the direction has changed? This is the direction in which the wave was coming, and this is the direction in which the wave travel. So moving from deep to shallow, what we'll observe, the wavelength, the distance between the wavefront decreases, speed also decreases, and if it is making certain angle with the surface, its direction will also change. And opposite will happen if the wave is traveling from shallow region to deep region. So you will find questions, sometime it is from deep to shallow, sometime it is from shallow to deep. So example, a wave is there in a shallow region and you want to complete. So right now it is in a shallow and it is moving in a deep towards a deep region. So moving from shallow to deep, what happened? The speed and the wavelength both should increase. So how we represent an increase in speed? So if I draw horizontal line, it means it is the same speed. If I draw like this, it means a slowdown. So because the speed increases, so I should draw other way around. And the direction in this example, the direction is also changed because the direction of the wave is perpendicular to the wave front. So this is how the direction has changed. Is it clear? The two figures about the wave. Any doubt in this part? So as the wave travel from one medium to another, it changes the speed and wavelength, but the frequency remain unchanged. Then the third property is known as diffraction. What is the meaning of diffraction? As you can see from this image, that diffraction means spreading of the wave. When the wave spread, when it is passing through the gap, the wave spread, and this spreading of the wave, what we call that as diffraction. So Example, as you can see here, when the wave is passing, like the gap is a small gap. So when the wave is passing through a gap, this is a large gap. So when the wave is passing through a large gap, what we'll see, we will see a small diffraction spreading of the wave. As you can see in this image, this is what we'll see on the screen. So as the wave is passing through the gap, as a result, what we see, a small amount of wave is able to pass through. When the wave passes through a gap and small amount of wave spread out, what we call that as a small diffraction, because small quantity or small amount of wave is able to pass through. But if the gap is smaller, like small gap is there, so what we'll see or what we'll observe, as a result, we'll see greater diffraction or greater amount of wave spread out. So here you can see in this image, when we are passing through a narrow gap, when we are passing the wave through a narrow gap, as a result, what we see, the greater amount of wave is able to pass through. So when the gap is smaller or a narrow gap, we'll have more diffraction as compared to a wider gap. And what is the meaning of diffraction? Diffraction means property of the wave to change the to spread out when it is passing through a gap. Same way, some of the waves, when it is passing through the edge, it also diffract or changes the direction slightly. We also call that as diffraction. Remember these terms for edges. When the longer wavelengths are there, they have more diffraction. But for gaps, when small gap size or gap size is same as the wavelength, then we'll have maximum diffraction. Now we'll do some questions related to our topic. So three topics. One is reflection, the second one is refraction, and the third one is diffraction. We'll do questions related to our topic, so it will improve your understanding. Just a minute, I'll share with you the question. So this exercise is related to the properties of the wave. So as we have discussed the reflection, refraction, diffraction, as well as the two types of the wave, longitudinal and transverse. This is related to the examples. Which row shows the nature of a light? Light is transverse, sound is longitudinal, and X-ray is transverse. So it matches with transverse, longitudinal, transverse. So it matches with option C. You have to learn the example. Most of the waves are transverse. Only sound wave and wave in a compressed spring is longitudinal. Now this question is related to diffraction. As we have discussed, for diffraction to occur, the gap size should be, for maximum diffraction to occur, the gap size should be equal to wavelength. That is, if we want the diffraction to be maximum. So which one will have the different wave hits the barrier? The waves will diffract in which diagram the greatest spreading or diffraction occurs. So greatest spreading or diffraction is there when the wavelength is equals to gap size. So what is the right answer? Maximum diffraction when the wavelength is equals to gap size, or the gap is smaller than the wavelength. So when we check for A, wavelength is 1 but the gap size is 2. So it's the wavelength is smaller than the gap size, so it will not have too much diffraction. When we check option B, the wavelength is 2 centimeter and gap size is also 2 centimeter. So it will have the maximum diffraction. As the wave will pass through, it will spread out more. In question 3, which row on the graph shows an amplitude of the wave? So which one is representing the amplitude? Label A, B, C or D? You can use the chat to state the answer. Which one is representing the amplitude? A, B, C, or D? Amplitude is the height or the depth of the wave from the mean position. This is the mean or the center position. So the height of the wave from the mean position, that is B, is the correct answer. Why not A? A is actually height plus depth. So that's why it is twice. What is D? From one trough to another, it's actually a wavelength. And what about C? It's a half of the wave or half of wavelength. So that's why B is the next one. The diagram represent a plane wavefront. So the diagram represent a plane wavefront being diffracted. This is a small diffraction. What we want, which pair must increase the amount of diffraction? If we want to increase the amount of diffraction, we want to make the wavelength. If we want to make a maximum diffraction, we want the wavelength should be equal to the gap. That is what we want to do. So here, when we measure the wavelength and the gap is bigger. The gap size is bigger and the wavelength is shorter. So what we should do to increase the diffraction? So we should increase the wavelength and we should decrease the gap so until it matches with each other. Like here the wavelength is shorter and the gap size is larger. To make it more diffraction, the wavelength should increase and the gap should decrease. So what is the right answer? Increase the wavelength and decrease the gap size. So C will be the right answer until it balances with each other. Because the question is which pair, we have to select a pair, like what should happen to the wavelength as the wavelength is smaller. So we should increase the wavelength and the gap is larger or bigger. We should decrease the gap. That's why C is the right answer. Is it clear discussion? Because in the example here, the for a maximum diffraction the wavelength should be equal to gap size, but here what happened, the wavelength is smaller and the gap is larger, so we should increase the wavelength and decrease the gap to make it diffracted more. The diagram represent a plane wavefront, as you can see here. Which diagram represent the reflected one, like which direction it will reflect, A, B, C, or D? So it changes the direction, like this is the direction in which the waves strike and then it will bounce back. So yes, you can use a screen annotation. So C is the right answer. Okay, in question 6, the plane wavefront, they are moving, they're in a shallow region and they now travel in a deep water. In a shallow, it is moving slower, and in a deep it is traveling faster. So if it is traveling faster, how I should draw the wavefront? The wavefront, because if it is traveling in the same direction, like if its speed does not change, then it will travel in this manner. But as it is traveling faster, the distance or the gap size increases. So what is the right answer here? That is C. I'll share another link and continue this discussion.